Yes, thank you very much. Super happy to be here. Yeah, so I'm a PhD student in Munich at the LMU University, and I'm going to talk today about the synchronizations in PyTorch. Come in. So, who is this talk for? I guess it's good for anybody who is writing PyTorch in their day-to-day and is using GPUs to accelerate their workloads. In this case, this talk is for you. I want you to take away, leave the room understanding what are these synchronizations that I talk about, and why they are important, namely because they silently slow down the performance of your application. And it's not that your code is incorrect. Your code is still going to be correct, but it's just going to leave a lot of speed on the table. And finally, I want you to be able to spot them and then to fix them. So the overview is going to be, we're going to be looking at a basic training loop, like everybody has probably seen before. And this is going to have a synchronization, so that's problematic. We will then dive into, look at some real profiling traces so that you can see how, if you use real profiling tools, what will you see in this case of synchronizations with NVIDIA Insight systems. Then we will dive a little bit deeper into more subtle patterns that trigger synchronizations. And finally, we will have a look at unit testing to check that whether your code contains synchronization so that you can be confident that you are synchronization free, that your code is synchronization free. So let's get started. This is the familiar training loop that you might have written yourself for your machine learning project. So basically, we have a loader where we're loading batches of data. We are calling the model on this batch of data, like getting some output, then based on this output, computing a loss, then doing a backward, and using this optimizer to step to change the model weights. And finally, you probably want to have a look how the loss is doing. You want to see it going down, so you print the loss. And we often start by writing this on CPUs to test and make sure that it's working correctly. Then we move it on the GPU, and we see that indeed it gets faster, but it's not as fast as we expected it to be. And NVIDIA provides this command line tool that you can use, NVIDIA SMI, and it will show you like the metrics around your GPU, and you might be somewhere around 50% utilization, more or less. And it definitely is probably not 100%. And you check different things, and you see that, well, everything seems to be correct, so what is it that's happening that's slowing down your code? And the hint is obviously, well, the synchronization. Good, so that is the familiar training loop. Now I want to take a step back and think about or explain how the GPU actually is working. So how is the CPU and the GPU collaborating? And hello, I'm back, right? The GPU is actually asynchronous. So the principle that you need to keep in mind is the CPU is bossing around the GPU and telling it what to do. And what we see here is a timeline with GPU and CPU. And the CPU is scheduling these operations, these PyTorch operations, to be queued and executed by the GPU. So you see, these are the operations that we had in the loop: zero grad, forward, loss function, backward, and step. And it takes a little bit of time for them to move to the GPU and then start on the GPU. And then since the GPU is the one actually doing the work, it takes a longer time. Each operation takes a longer time on the GPU than it takes it to be just scheduled from the CPU. And importantly, this means that the CPU finishes scheduling the operations before the GPU finishes executing the operations. And this is a healthy thing. This is what you actually want to have. And it's also very interesting to see that the CPU is done, like here at this step, it's already finished scheduling. The GPU is still in the middle of the forward pass and hasn't even started to compute the loss function, backward, or optimization step. This is why we say, or it is said that the CPU runs ahead of the GPU because it finishes earlier. And if you were to naively time how long it takes the CPU to finish all the operations, then you would be misled to think that it's very fast while the GPU is still working on getting the actual work done. And the question is, so what is a CPU-GPU sync? So it happens when the CPU gets blocked and it has to wait for data to come back from the GPU. For example, when the CPU needs to take a decision based on that data. So here we have an example. So we have in our code something like, if this CUDA tensor is larger than 0, then do something, otherwise do something else. Right? So the data resides on the GPU, but the CPU needs that information to take the decision. So it has to move this information back. And this is another timeline where now I have said, let's call them up1, up2, up3. And up1 and up2 are scheduled normally, but up3 cannot be scheduled until the CPU gets this information back from the GPU. So what we see here is that the CPU blocks. It has to wait. So all this time here is spent doing nothing, waiting for the GPU to send information back. Then it can schedule up3 and send it back to the GPU. The GPU will be waiting in the meantime, doing nothing. So these are the bubbles on both sides of the hardware. On the CPU side, you have bubbles. The GPU side, you have bubbles. And this is going to slow down your code. So when is it happening in our training loop? It happens precisely here when we want to print the loss that we currently have, right? This call to .item forces the CPU to fetch that information from the GPU and synchronize. And this is happening on every iteration. So you schedule these 5 operations, or I don't know how many they are, schedule them, synchronize, schedule them, synchronize. And one simple fix would be just to say, well, I synchronize just every 100 iterations. That means these 100 iterations will be just batch scheduled, executed tightly without bubbles. And I still want to know my loss sometimes, so I just print it out. There are also solutions where you asynchronously fetch back the data from the GPU, but that's a bit more involved. All right, so let's say we understand these timelines that I showed you, but you want to actually see it with real tooling. So we can use the NVIDIA Insight Systems Profiler. And I prepared a snippet of code that's simpler because it doesn't have the backward pass and the optimization step, which complicate the picture. So in this simpler example, it's also a loop, but it consists basically of a slow operation and a quick operation, and then an optional print, which is going to either trigger the synchronization or we leave it out and there is no synchronization. And if you have an NVIDIA GPU, then you probably have this nsys command available, which you can create a profile. And this is basically the program that we're profiling. It's available on this GitHub gist if you want to try it out yourself, maybe later today. And what we're going to see, this is a screenshot from the Insight Systems Profiler. It has, again, 2 traces. So there is a CPU timeline, which is this one. And on the top, you see a GPU timeline, which is the longer one. That's why I put the CPU on the bottom, even though it would have made intuitively more sense to put it on the top. But this is just how it's structured. And I want you to notice what is most striking immediately is that the CPU timeline is a lot shorter. So it is running ahead. It's scheduling all these operations. Slow, fast, slow, fast, slow, fast, slow, fast. Scheduling everything quickly. And then the GPU starts working on the stuff a bit later. And the slow operation is the yellow one. I think you might be able to read it. And the quick operation is the blue one, which is shorter. And they're operating back to back. Here on the top, this light blue bar is the GPU utilization. So you see that it has a little bump here, a little bump here, but in general, it's continuous. So you're getting 100% utilization from here until all the way until the end. And this is a healthy run. So this is no synchronization whatsoever. The print statement is disabled. And now, if we enable the print statement, we have a synchronization. So this is the case where this is the same screenshot, but for the workload with synchronization. And what we see here is, again, the two timelines, but the lower timeline of the CPU is a lot longer, and they both end up around the same finish line, so to speak. This means the CPU is not really running ahead, but rather it's being delayed. And here on the bottom, you see these green bars, which are completely new. And what they say, if you can read it, it says CUDA stream synchronize. So while this green operation is running, your CPU is doing nothing else. Or basically that's your waiting time on the CPU. It's waiting for the information to come back from the GPU. The GPU operations look very similar. So you still have slow operations followed by quick operations, but you have these gaps in between. And importantly, on the top, you see the utilization has some gaps there. And that's precisely where the slowdown is coming from. So you have, on the top, you have the slowdowns. On the bottom, you have the green slowdowns. And this workload becomes like 400 microseconds slower. It could be a lot more. This just happens to be a lot of matrix multiplications, which occupy the GPU very well. OK, so we say we understood this. We want to write fast code, so we're going to avoid some of the idioms that trigger synchronizations. So there is a PyTorch performance tuning docs, which has a section about this specifically, and it mentions these bullet points over here. So avoid .item calls, printing CUDA tensors, avoid this .cpu call, don't put it in conditionals. And I think once you've seen them, it's easy to memorize them and be like, OK, those are easy to avoid. I can do that. But the more interesting part of this talk is that there are more subtle idioms or patterns that trigger synchronizations as well. And those are related to dynamic shapes. So let's go through some of these dynamic shapes and understand what's behind them. These operations may look harmless, but they create also synchronizations without you intending to, right? So let's start with this one. This is a case where both T and mask are tensors on the GPU, torch tensors. And this is basically a boolean indexing, right? So mask is an indexing. You're selecting a subset of the T tensor. I think it's a very common operation. You do it in NumPy, you do it in Torch. This is very, very, very common. The problem here is that the length of x, how large x is, will depend on how many truths there is on the GPU side, on the data that's living on the GPU side. A very similar pattern is this one. This is slicing. So if k is just an integer that's living on the GPU, let's say 10, 20, it doesn't really matter, and you slice another torch tensor with it, this would be like selecting the first 20 elements of this tensor, then the CPU will also not know how long the resulting tensor will be without fetching that information back from the GPU. And more Torch APIs have the same problem. So this is non-zero. What it does is it gives you the indices of non-zero values. And how many non-zero values are there in a tensor? Well, that depends on the data. The same with unique. This is like calling set on a list in Python. So how many unique numbers are there in a tensor? Well, that depends on the tensor and its data. So what they all have in common is that they synchronize because PyTorch needs to allocate this output tensor x, and it needs to know the shape in advance. And if this shape depends on GPU data, the CPU must ask the GPU. And if you think about this boss and this relationship of boss, the CPU is the boss, but if the CPU needs to ask the GPU, then it's not the boss anymore. So you're having this inversion of the who's the boss that usually both have. This is basically what I mentioned before. So rule of thumb for you or mental model should be if your tensor has a static shape that is known in advance, then you can have async operations on it. If it definitely has a dynamic shape, then it's likely that you will have some operation that triggers a synchronization. There are ways to fix this issue with dynamic shapes. So, for example, this function from Torch called repeat interleave, it has an optional parameter that you can pass that tells Torch how large the output will be. So you tell it the output size is total. This can be an integer, let's say 10, 20. And then, since Torch doesn't have to ask the GPU anymore for the size, it can allocate this without a synchronization. And the code runs through without synchronization, while this idiom does trigger a synchronization. So Torch gives you some tools to work around this and avoid the synchronizations. Yeah. So you try to use the APIs that allow you to pass the output size. This variable saying like what is the total size should definitely not be residing on the GPU, so keep that on the CPU side. Otherwise, you will have a synchronization again. And the padding is also a solution, so which I didn't, so I'm not going to delve into that a lot, but you can use padding to avoid dynamic shapes. And yeah, finally, let's talk about unit testing. So we saw that that you can see the synchronizations with a profiler, that you will see these long calls called CUDA stream synchronize. But do you need to do this every time just to identify a synchronization? The answer is no. There are tools to do this quicker without having to spin up a profiling. And for that, PyTorch offers an experimental debug mode that flags every synchronization in your code. So how it looks like is like this. torch.cuda.set synchronize debugging mode, and you can set it to warning, such that if you take a CUDA tensor and you trigger any type of synchronization on it, it will raise a warning for you. So you can activate this, run your code, and if you see a warning, then you know, well, there's some synchronization somewhere. You can set it to a strict mode with error by passing error, and then this same pattern will actually raise an exception. And that is actually quite useful, because then you can use this pattern in unit tests. So what you can do, here what you see in this case is it's a unit test that is loading some inputs and then passing those inputs to something called my PyTorch function. It can be really anything. It could be your model. It could be some function that you wrote yourself. And then there is some correctness check. And what I have done here is to add a decorator that says fail on GPU sync. So this unit test will fail if my PyTorch function has a synchronization. And what's happening under the hood, yes, is there's this decorator. Before calling the function, I set a debug mode to error, such that it raises an exception on the function. And afterwards, you deactivate it again. And the cool thing is that you're not touching this function under test. You're only modifying unit testing code, so the production code stays clean of this experimental API. And you can test also code that is coming from a library right, or that is not your own code, you can still test it for synchronizations without modifying it at all. Yeah, so the takeaways from this talk are the asynchronous mode is the default for operations launched on the GPU. The CPU is supposed to run ahead. That's healthy. The GPU is supposed to stay busy with work. Synchronization is when you are blocking the CPU while it waits for the GPU, inverting this bossy relationship between both. And there are some really clear, obvious triggers that you should easily remember, like item, print, .cpu, if else branching. And there are more subtle triggers that you might have to reason about with dynamic shapes. And there are obviously solutions to that, which the optional parameters that I showed, but also padding, or just, you can still sync. It's fine. The world is not going to end by syncing. But you can do it just less often. And finally, obviously, if you want to unit test your code for it, you can do so. And PyTorch provides the APIs to test this on your own code. That's it. Thank you. Thank you very much.
Thank you very much for your presentation. Now we have some questions for you from our audience. One of them is, how much of an issue is this on unified memory architectures such as NVIDIA GB200 or Apple M series?
That's a very good question. So my understanding is that in unified memory, you supposedly don't care anymore where these tensors are. But I haven't actually gotten my hands on one of these systems to be able to tell how much of an issue it is. I assume it's less of an issue. But if you have one of these machines, reach out to me.
Thank you very much. Do tools such as TensorBoard sometimes introduce an expectant synchronization?
Good question. So I haven't looked at the code of TensorBoard. My understanding is that they are very much aware of this, and they fetch these. They fetch those. So they do this async solution, basically, where they are moving the memory asynchronously from the GPU to the CPU. But I'm not sure. I would assume they do. So yeah, it would make sense. So you're not synchronizing on the hot loop of the training.
Okay, thank you. Why does the CPU need to know the sizes if the resulting tensors are created / continue to live on the GPU?
Yeah, that's a good question. I don't know. The short question is I don't know why it necessarily needs to know the shapes. And why, if you just tell it the shape, it can just go merrily forward. So that's a good question. I don't know. I would be necessary to look into maybe the memory allocator or something like this.
Probably the memory allocation on GPU is the boss is the CPU, and he needs to tell the GPU how much to.
Yeah.
The GPU can't do it by itself.
Yeah. Agreed.
Thank you. Do you need to run the unit test with your wrapper on a NVIDIA GPU to detect the sinks, or will PyTorch also raise an error on CPU?
I haven't tried on the CPU. Interesting question. I'm not sure if the concept of a synchronization even exists if you're running entirely on CPU. I don't think so. So probably it won't do anything.
Okay. One more. Is synchronization also a problem in, for example, ONX models? Would NVIDIA Nsight also work in this case?
ONNX? Mm-hmm. I'm not familiar with the ONNX runtime, so I don't know much about it. Sorry.
Okay, thanks. Do all dynamic result operators have allocation hints, or are there known exceptions?
This is, so I talked about this repeat interleave, and this is, I would say, one of the few functions that offers this output size optional parameter. Let's have a look at the rest. I don't think the others have this, but it's up to, I mean, the documentation is there and you can look it up and then try to select always the API that offers you this, the path to pass the output sizes.
Thank you. The last question is, do we need CUDA and PyTorch versioning?
In PyTorch what?
Versioning.
Do we need CUDA in PyTorch versioning?
And CUDA and PyTorch versioning.
Yeah, so this was entirely tested on CUDA devices, so GPU devices. I haven't tested it on other GPUs like AMD or whatever, but I expect similar problems if the devices are separate. So, yeah.
Okay, thank you very much. Thank you for the presentation and answers.